So welcome to lecture 3. This one is going to be mostly about metals, and with metals, things turn out to be harder to derive precisely than for insulators. For insulators, the advantage of a gap means that adiabaticity is well defined and so on. But the good news is with metals, there are some fairly simple things I have to tell you where even our basic picture of like textbook level metal physics has changed a bit because of Berry phases and things like that. So, for example, the semi-classical equations that you'll read in Ashcroft and Merman for how a wave packet moves in a metal, and probably in other old books as well, are actually wrong in two slightly different ways, and both of those are important to understand some physical effects. So let me remind you what I said about polarization, and mostly I put up this slide again because of the comment at the bottom to kind of explain how you could guess that something like the wave function would be important for polarization. And again, I'll start on the board. Start on the slides and try to use the board a bit later on, especially if there are questions. So the polarization is the loop integral of A, I claimed, and that's an argument since polarization is related to where charge is sitting, that the Berry phase must have something to do with that, and we're going to see how that works. So why is it maybe reasonable that polarization should have to do with the wave function and not the band structure? So the band structure, suppose I have a material that has time reversal symmetry but breaks inversion, like most ferroelectrics say. Then the band structure is still looking symmetric. In other words, E of k is equal to E of minus k just from time reversal. So in other words, if you just look at the band structure and you see it's even in k, it doesn't actually prove that the material is inversion symmetric. What it means, though, is that any physics that's going to come from broken inversion can't come from E of k. It has to come from something else. And at low energy, that's usually the Berry phase. It's something having to do with the wave function, the use of k, rather than the energy dependence on k. Okay, so with metals, this is the first example of something added to what you'll find in textbooks. And actually, even back in the 60s, there were a few people claiming that this term should exist, but they didn't really have the modern way of writing it, so they were kind of ignored until more recently, until the 90s. So let me motivate the first term, first of all. So when you go into a metal, we know that E depends on K in a different way from in vacuum, and therefore the group velocity of a wave packet is modified. So this part you will find in all the textbooks. Even this, you have to think about a bit more carefully in a magnetic field, it turns out. But for now, let's leave that term the way it is. And then there's an extra term, which is sometimes called the anomalous velocity or the Karplus-Luttinger velocity, after the people who were thinking about it in the 60s. Formally, this makes the equation look nice. This is, if you want, like a potential term in momentum space, and this is like a magnetic field. I didn't write the momentum equation, but the momentum equation would be like a Lorentz force law. It would have electric field plus magnetic field. So this term is kind of like a magnetic field in momentum space. And let me give you a quick argument for why something like that has to be there. At least in a material maybe with more than one atom in the unit cell, there could be a term like this. So that's the same F we talked about before. That's the Berry curvature. A and B are just band indices. So this is saying there's an extra velocity coming from F dk dt. So remember, F is roughly, it is at least a k derivative of A. Let me not worry about all the indices. That would get complicated. So that term, in other words, F dk dt is like, well, dA dk dt. And this looks like a total derivative in time of A. Well, we said A is related to polarization. So that's a change in polarization in time. To be precise, it's a polarization divided by E. So that's like a current over a charge, which should be related to a velocity. It should be a velocity times a density, strictly speaking, but we're thinking about one electron at the moment. So that is a rough argument for why such a term should be there if we really believe that A is connected to polarization. Let me give the sort of standard intuition for why this works. So suppose that at one momentum, suppose I've got a unit cell with two atoms in it, A and B. and they sit at different points in the unit cell. Then maybe at momentum k1, maybe the electron block state, the U sub k, is mostly sitting around here. And maybe at momentum k2, the electron block state is mostly in a different orbital sitting around there. Because we know that in a tight binding model, say, what combination of orbitals I have varies with k. So then in between, as momentum goes from k1 to k2, maybe in between it's somewhere like this and so on. The point is there's a continuous path of where the orbital sits as k evolves. And therefore, the center of mass of the electron is moving within the unit cell as k1 goes from k2. So we think of the second term as there because the electron is not a point particle. If the electron was really a point particle with no internal structure, we would just have the first term. And only the first term is there if I have both inversion and time reversal symmetry, or if I have a single atom in the unit cell. Some minor comments. But in general, the second term is there because there's also a velocity which is electron motion within the unit cell. It's the fact that the wave function is changing with momentum. So that's this Karplus-Luttinger anomalous velocity. It's maybe the simplest consequence of the fact that the Berry phase has something to do with where the electron sits. And the reason why people studied it a lot was the old example of where geometry is important in metals, but it doesn't give you anything quantized. So what I want to do in this last lecture on metals is sort of present the old stuff that you can understand semi-classically in terms of the Berry phase, and then some newer results are that there are more quantized things even in metals, which is kind of a surprise, although I'll try to convince you it's not actually that surprising in the end. Yes?
You said there's a corresponding equation for momentum, and these equations, if you put them together, are they still Hamiltonian?
Yes, they are. You have to, if you want to be precise, there's an extra, you have to use the right volume element of phase space, which looks something like that.
So you change the geometry of phase space?
If you have both non-zero Berry curvature and non-zero magnetic field, then you just change the volume. But there is a way to make the equation still Hamiltonian. Good. Other questions? Yeah.
So in order to justify this second term, do I need always to think that I have a unit cell with many centers, or?
I think that's right, because if you only had, okay, think about a tight binding model with only one atom in the unit cell, then U sub k would just be a one-component vector, and there's really no Berry phase allowed by that. So I need at least a two-component Hilbert space for the Berry phase to be non-zero. So one question, if I had two or three orbitals, but they were all in exactly the same spatial location, I think that this term would vanish. For example, you'd have an inversion symmetry, and if you also, at least if you had time reversal and that structure, this would vanish. But I haven't thought about it in detail. Good. Other questions? Okay, so the main consequence of this historically was the anomalous Hall effect, which I'm not going to say too much about. Ivo Souza, who's here, is an expert on this. I'll tell you about one of his predictions in a second. So the basic idea of this is that if you take a metal like iron, which is also magnetic, so Hall, for example, studied that back in the 1890s or so, and he found that that has a Hall effect in its own magnetic field, if you like, or because it breaks time reversal by itself. You don't need to apply an external magnetic field, really. Or if you do apply an external magnetic field, it's basically just to make sure you know the polarization of the iron. Okay, so what you measure is, in general, complicated, and this was a very hard field. You can tell this is a beautiful long review article from 2011, and by the time they get to figure 47, the phase diagram is still speculative and schematic, so that's a hard problem. In general, there's a term that we like because it's geometric. So this is basically the same integral that if I were in a 2D insulator would give me the Chern number, the integer Hall effect. In a metal, I only do it over the Fermi sea, so it's not quantized, but it's still a very nice piece because this term only depends on band structure and wave functions. It doesn't care about disorder. So we call this intrinsic. If I make a material very clean, it turns out that sigma xy is actually dominated by the details of scattering on the Fermi surface, so it's less universal. And if I make a material very dirty, I start to get localization type physics, but there's some intermediate regime where indeed this is the dominant term. And one experimental proof of that Ivo worked out is you can take materials that have an anisotropic band structure like cobalt and calculate how the anomalous Hall tensor should depend on direction if it's dominated by this, and you do see that experimentally. So that's at least strong evidence that this kind of term dominates. But from our, if you like geometry, this is good. If you like topology, this is maybe not so great because this is not going to be quantized. I'm no longer integrating over a closed manifold. I'm just integrating over the Fermi sea. So this is nice. It says geometry is very important in metals and so on. Karplus and Luttinger worked this out, and we think they're right. But we'd like to find other examples that are a bit more topological. So I'll mention one effect because it's going to come back later. We worked on this in 2010, and at the time we thought it was a nice demonstration of the semi-classical Berry phase, but had nothing very topological and so on, and then more recently we changed our mind. But here's an effect, if you like, that is nice. It had been measured for a long time, maybe 20 years or so, particularly by a group in Regensburg, led by Ganichev, and they thought it was mostly because of spin-orbit coupling, and then to their credit, they basically had done the experiment in gallium arsenide, which has fairly strong spin-orbit coupling, relatively strong. Then they did it in silicon, and they thought the effect would go away, and it didn't really go away. So so they concluded that maybe this is not entirely spin-orbit coupling, and we think that's correct. Instead, it's a Berry phase effect, and here's the effect. So suppose I'm just thinking about semi-classical picture of a metal with some disorder, but not localization. Then if I apply a little bit of electric field in a metal, let's say the black circle is the ground state of electrons, then what this force does, it moves the electron distribution a little bit away from the ground state, but then there's some relaxation, so it doesn't keep accelerating forever. I reach an equilibrium which has some non-zero current. So if I just let the system not evolve in time, that would be my ground state, it would have a current. So now I want to think about low frequency circularly polarized light, and the experiment is done with terahertz. So circular polarization means, let's say this is the state at time 0, but I slowly rotate the gray circle around. That would be right circular polarization. Left circular would be like that. And you can probably see that the ordinary velocity will average to 0. But if you take the right kind of materials which break inversion symmetry, for example, if you cut your gallium arsenide quantum well the right way, you find that the anomalous velocity does not cancel out because basically dk by dt is negative here, and when I come around to the right side, it's positive. But the Berry phase averaged over the electron distribution also changes sign. So basically this experiment, in hindsight, is a way to cancel out the normal velocity and just pull out the anomalous velocity. And the only ab initio calculation I've ever done myself, I have to admit, was calculating the strength of this effect. And maybe because I knew what I wanted the answer to be, it came out to the right magnitude. But at least I think at the moment, it's believed that at low frequency, this is a possible explanation for the experiments. But here, what you get is the strength of the Berry phase, say, and there's nothing particularly quantized about it. It's like that anomalous Hall effect case, except maybe there are fewer contaminating other effects. So now I want to talk about linear optics for a little while, and eventually talk about nonlinear optics as well. I'm going to go a little bit quickly through the first part, which was kind of our motivation. But basically, the message I want to make is that, first of all, if you want to understand linear optics of materials like Weil semimetals and so on, there's one more ingredient in the semi-classical equations that we kind of missed, so we need to put that back in. And then second, in a way, this is a negative theorem for Weil semimetals. We want to claim that the so-called chiral magnetic effect is either 0 in some case, depending on how you define it, or when it's non-zero, it's not exactly very topological. It's not specific to Weil semimetals. So if you want, my main discussion of linear optics is going to be about, first of all, another piece of semi-classics, and second, why you need to go to nonlinear optics or else magnetotransport if you want to see something very unique to Weil's. Because just to remind you, my mission in these lectures is to try to figure out, once you've got a topological phase, what electromagnetic things should you look for to know that it's special? And we haven't yet done that for Weil semimetals. In fact, I don't think Weil semimetals have been discussed too much in the theory lectures so far. I'm sure Andre Bernevig will say a lot. So anyway, let's get started. So this was all motivated by an experiment on the cuprates that we still don't understand, so I'm going to skip that. So let me just give a little bit of background and kind of illustrate where we're going. So where this begins is by thinking about which materials can modify light as light passes through. And I'll explain how this is actually the same thing as the so-called chiral magnetic effect in a second. The reason why this was important is there are two geometries you might use to study the rotation of light. One is you send light through a material, and maybe you see that the polarization rotates. So you've probably heard of the Faraday effect. If you've got a magnetic material, then the polarization rotates. If you've got a chiral material, something, for example, made up of sugar molecules that are like spirals, then you'll also find that the polarization rotates in transmission. When you bounce light off of something, then light can rotate if you bounce it off a magnetic material. It turns out that it can't rotate if you bounce it off a non-magnetic material. And what was the mystery that we were kind of confused by is that there's a famous Stanford experiment on high-temperature superconductors that claims to see rotation in the reflection geometry, the so-called polar Kerr effect, and we basically just verified with microscopic calculations the general idea that this can't happen if you have a time reversal symmetric material. Okay, so there's a side comment. But that sort of led us to thinking about if you've got a metal and you're studying at low frequency, what controls what happens to light when you go through the material? And then we realized that without exactly knowing what we were doing, after some conversations with Ivo and others, we realized this is actually something about the chiral magnetic effect in disguise. So here I'm going to sketch the answer and then kind of illustrate how we got up to it. So the idea of the chiral magnetic effect was the following. I think I have a slide or two on why this was conjectured, but since we're going to say that you have to be very careful about writing this, the idea was that if you took some special materials, including Weil semimetals, and I'll come back to what a Weil semimetal is, you could have a current induced by a magnetic field, which is very unusual. In fact, in equilibrium, I don't think this is possible. It's generally believed, this is sometimes called Bloch's second theorem, that there's a difference between electric and magnetic fields. In an electric field, a system will stay out of equilibrium and a current will run, while in a magnetic field, a system can reach equilibrium with no macroscopic transport current. You could have something like a ring current that never transports charge anywhere. So this was a surprise that maybe you could induce a current purely with magnetic field, and I think everyone agreed pretty soon that this had to be zero at equilibrium. But then people started saying, well, what if you let this oscillate in time? And I'll explain why that is a different limit. It has to do with the non-commutativity of Q goes to 0 and omega goes to 0 limits. Anyway, so if you let this oscillate in time, you do get a non-zero answer. But the non-zero answer is not actually a Berry phase or topological thing, but it's quite interesting. If you do it in a metal at low frequency, and here our version of this is from 2016, this formula says I can compute this response, and it's basically the response to a low frequency wave, which is why it's the optical rotation problem in disguise. So what I want to build up to is that it's given by integral over the Fermi surface of Fermi velocity times a fairly new quantity, at least for me, which is the orbital moment of a Bloch electron, and how that depends on K. So this is sort of an outline of where we're going. That basically we don't think there's a chiral magnetic effect as originally written. There's something we called gyrotropic magnetic effect, but it's really a measurement of orbital moments. So what's a Weil semimetal and why are they trendy? Because, yeah, what I'm saying is that basically by trying to understand optics, we wound up understanding these materials a little bit better, or at least understanding some previous work on them a bit better. So two of the big topics in condensed matter nowadays, you've probably noticed, are Majoranas and Weils, and they're both different ways of taking half of the Dirac equation that were figured out soon after Dirac. So Dirac wrote a 4x4 matrix equation for the electron in 3 plus 1D. And kind of remarkably, for a long time, we had graphene, say, which is 2D Dirac electrons, but we didn't really have materials that had 3D linearly dispersing electrons at the Fermi level with nothing else at the Fermi level. That was mostly a materials problem. The theoretical concept was discussed a lot, even for solids, in the 1930s. There's a famous condensed matter theorist named Conyers-Herring who actually did this for his PhD thesis, I think with Wigner in the 1930s. So anyway, we now do have examples of 3D Dirac fermions, and what's maybe even more exciting is Weil pointed out the following, that if you specifically are thinking about massless particles, then there's a way to separate out the Dirac equation, which is the following. If you've got one natural basis to work in for particles, say, is the helicity basis, where you've got right-handed vectors where the spin is along the direction of motion, and you've got left-handed vectors where the spin is opposite the direction of motion. So normally, you transform between these bases if you've got a particle if you boost to a frame moving faster than the particle. So you can mix right-handed and left-handed particles that way. If you have particles that are moving at the speed of light, like massless particles, then right-handed and left-handed are truly separate, and they don't mix. They're really two separate particles. And we thought for a long time that the neutrino was a Weil fermion in the standard model, and now it turns out not to be true, because people discovered that neutrinos have mass not all that long ago. So now we think that there are no Weil fermions in the standard model. There are no particles with this definite right-handedness or left-handedness, but there are materials, and these have kind of a topological interpretation in terms of the Berry phase. I think Andre, who was one of the discoverers, will talk about the history of this, I hope. But anyway, starting around 2014, we have examples, both many theoretical proposals and even experimental samples of Weil fermions. So Majorana's I won't talk about, but you've already heard Majorana is taking half of Dirac by imposing that the particle is the same as its antiparticle. And those might exist in the standard model. We're not sure. The neutrino might be a Majorana fermion. Okay, so what's topological about having two bands cross linearly? And here, maybe it's useful to draw a picture. So remember what we said before about the integer quantum Hall effect. Integer quantum Hall effect was we can get an integer by integrating over the two-dimensional Brillouin zone, which is a torus, the Berry curvature, F, with whatever normalization you like. So that's a nice dimensionless integral because F, remember, has two k derivatives of u inner producted with itself. So that inner product is dimensionless, and then the two k derivatives cancel out d2k. So now we're talking about 3D materials. So how do we make something that might be dimensionless and quantized out of a 3D material? Well, you take your linear crossing and you imagine making a little sphere around that crossing point where the little sphere lives in momentum space. And then I look at the Berry flux through that sphere. That is also now, instead of an integral over a torus, it's an integral over S2. But that still gives you a Chern number. And it turns out that these two bands generally will have some non-zero Chern number. And there's one constraint, which is if you add up the total Chern number of all the crossings at all energies, that has to be zero. This is known as the Nilsson-Ninomiya theorem. But in general, you can have some positive and some negative. They can be at different energies or positive energies depending on symmetries and so on. And one way that while semimetals were confirmed experimentally is there is an interesting surface state, kind of like in topological insulators, but different. If you go to the surface and you look at the projection of these crossing points to the surface, then there is a Fermi arc, say, between these two at the top surface and another Fermi arc between these two at the bottom. So a way to look about what happened, in the topological insulator in 3D, we took a normal Fermi surface, which would have two sheets because of spin, basically, and we put, say, the right chiral at one surface and the left chiral at the other surface. So we cut the Fermi surface in half. Here we're cutting the Fermi surface in half in a different way. We cut the Fermi surface into two arcs, and we put one arc at the top and one arc at the bottom. And there's a neat experiment by my Berkeley colleague, James Analidis, that claims to see the following very strange kind of quantum oscillation in a magnetic field. You can see electrons that move along the Fermi arc, if you remember your sort of quantum oscillation experiments to measure Fermi surfaces, electrons in a magnetic field kind of move along the Fermi surface. Then it comes here. The only place it can go is through a thin sample to the other side, do the rest of its orbit, and come back. So he has some experimental evidence based on patterning surfaces and so on that he can actually see the Fermi arcs even in that sort of transport. So I want to focus on bulk stuff that doesn't have to do with the surface, and it's been kind of a hard puzzle to find measurements that you can do just on the bulk of a wild semimetal that would tell you that it's something special. So the first category of things that people looked at, and this is where that chiral magnetic effect came from, is something called the chiral anomaly in particle physics. So I told you before that we know that the total of all the wild charges, so these wild points are like monopoles of the Berry flux, the total of all their monopole charges is 0, and that's a good thing because there would be an anomaly. Physics would be sort of broken if that weren't true. So for example, if we had a single wild point, then the consequence of that anomaly is that charge conservation is not satisfied. So there's a change in charge which is proportional to the wild charge times our old friend E dot B. So that's kind of interesting. If I have, say, positive and negative wild points, then applying E dot B should in principle pump charge from, say, one point to the other. There are efforts to look for that experimentally. I don't know how convincing it is so far, but the idea of the chiral magnetic effect was if we go into a crystal, maybe we could mimic the electric field by the energy splitting between positive and negative wild points. So it's going to be important for what I have to say that if you have a material with low enough symmetry, then the positive and negative points don't have to be at the same energy. And let me sketch quickly how that happens. So something about wild points and symmetry, which is useful for understanding the different kinds of materials that are proposed to be wild semimetals. So I said a wild point is a little source of Berry flux. Two of the symmetries we care about are time reversal is often a symmetry and mirrors are often a symmetry. So if this has a positive wild charge, say, time reversal will take this k to some minus k, but if you keep track of your minus signs, you'll find that this is also positively charged. So even with time reversal, you can have two wild points at the same energy that are both positive. But if I've got a mirror, a reflection symmetry, then I go from positive, well, now it's k reflected in the mirror. That goes from positive to negative. So mirrors in general are dangerous from the point of view of wanting energy splitting of the wild points. And this I won't work through the details in the interest of time, but maybe you can do that for yourself. So this was the idea of where people had sort of conjectured that maybe just a magnetic field could induce a current. And in understanding that, you wind up with a neat little bit of topology that I want to go through now, just using things we already know. So first of all, there's a neat topological identity that appears all over the place in this problem. And you can even see it in just as a check on semi-classics. And in fact, this uses the property that came up in the answer to Alex's question that you need to be careful about the phase space volume. Anyway, suppose I put on a magnetic field to my semi-classical equations and I want to compute the current induced purely by a magnetic field. The answer you get is 0, but only if you do it carefully. Basically, there's one part that comes from that correction to phase space volume. There's another part that at first looks different that comes just from semi-classic. So here, omega is what I called F before. Omega is the Berry curvature. F is now just the Fermi factor, so zero temperature is F0. So skipping over the details of this, trust me that you could work it out if you want to. You wind up that there's no magnetic field if this combination, basically the integral over the Fermi sea of Berry curvature dot group velocity, is 0. And that turns out to be true. And this topological identity, I don't think it has a name or anything, but it's also a key step in deriving the formulas I'll give in a second for optical response. And to kind of sketch quickly why that's true, because it was a bit surprising in that group velocity has nothing very topological in it, but Berry curvature does. Basically the fact that one of these is a curl of A, and the other is a gradient, you can show that it's 0, at least if you don't have to worry about singularities, and then when you worry about singularities, you use this Nilsson-Ninomiya theorem and you get there. And I don't have, unfortunately, the reference. We worked this out, and then we were sad to discover that the same identity appeared in a paper by Chan New, but we used it for something new. So now I want to come to 2 ways to derive the optical result that I flashed up. So one way is to do a lot of work and do quantum mechanics and do the Kubo formula properly. And this is the first of 8 pages of supplemental information doing that. The good news, and this is really an argument for semi-classics, is that you can get the same answer in 2 lines if you put in the right term in the semi-classical equations of motion. So we, at least for this paper, we were honest. We did the work, but I'm not going to go through it unless anyone really wants me to. I don't think I could that well at this point anyway. But anyway, yeah, so this is derivation of the expression for chiral magnetic effect and gyrotropic magnetic effect using Kubo formula. You use that topological identity and you use a bunch of stuff. So here's the basic idea, first of all, of why there are 2 different limits. One is 0 and one is not, and then how you can understand the non-zero limit semi-classically. So the 0 limit was apply a magnetic field and let the system reach equilibrium in the magnetic field. The non-zero limit is oscillate the magnetic field in time, but by the Maxwell equations, if you oscillate magnetic field in time, you also have an electric field, and without even trying, you're actually computing the response to an electromagnetic wave, which is why it's just the optical rotation problem in disguise. So the fact that there are 2 limits that don't commute should actually be familiar if you've ever done calculations in an electric field. If you first take Q goes to 0 and keep the field oscillating in time, that's how you compute the electrical conductivity. If you do the other limit, which is to first take omega goes to 0, so first make the field static at finite wave vector Q, that's the compressibility, which in general is a different thing than the conductivity. And the same thing is true for the magnetic field. The static limit is actually 0. The so-called uniform or transport limit is non-zero, but it's just the low frequency response to an electromagnetic wave. And people a long time ago knew what kinds of materials allow, say, optical rotation, which materials are chiral, which space groups, and so on. But people didn't realize, because they didn't have the needed ingredient, what microscopically, even in a simple metal, controls the strength of optical rotation. And the answer is going to be the second piece of how the semi-classical equations should be modified, which is the orbital moment of Bloch electrons, which I never learned about when I took solids, but I probably should have. And the idea is very simple. The expression is a lot like the Berry phase. In fact, for 2-band models, it becomes exactly the same as the Berry phase, and in certain other limits. But in general, it's a different object. So this expression would be the Berry phase. It would be the Berry curvature, F, if I got rid of this extra power of the Hamiltonian. And this is sort of making that traceless. When I put in this extra bit in the middle, what I get is the orbital moment of a Bloch electron at K. And here's a reminder of why that should exist, even though we never think about it. At least I never thought about it. I think it was only worked out properly around 2005 or so. The idea is, okay, think about tight binding model or linear combination of atomic orbitals. So we make up our wave functions in a solid out of, say, some s orbitals and some p orbitals and so on. And we know that in one atom, each of those has an orbital angular momentum, or it can, and therefore it has an orbital magnetic moment. So now we combine together our orbitals on different atoms, and it wouldn't be surprising if overall there's a magnetic moment, but that magnetic moment I get, so this is not the spin, this is the orbital moment around the atoms, that's going to depend on, did I make up my state of s orbitals or p orbitals or whatever, and that in turn is going to depend on k. So the reason why this is much more interesting, at least than a G equal to 2 trivial spin magnetic moment to me, is the following. This expression depends on k, which means it has a k derivative. So now when I put in a magnetic field, if I look at the group velocity, so not the anomalous velocity, just the thing that's the gradient of energy, now I should put in this extra energy, which is the orbital magnetic moment dotted into B. So if I apply a magnetic field, there's an extra contribution to the velocity, which is just the gradient of the magnetic moment, and that's non-zero. And if you do this really complicated, I mean, in a sense, it's non-relativistic quantum mechanics and perturbation theory, so maybe tedious more than complicated. But if you do that long calculation and you work hard enough, exactly this formula pops out. So you wind up computing the orbital magnetic moment without knowing it beforehand and realizing that what you're really getting is the correction to the velocity. Basically, it's kind of like that photogalvanic effect I talked about. All the terms related to electric field cancel out in this wave problem, but only this term survives, and it's non-zero. And that gives the formula that I wrote down a second ago, this thing, that the response at low frequency, the optical rotation of a material, which is the only sense in which chiral magnetic effect is meaningful, is given by the integral over the Fermi surface of the orbital magnetic moment. And for Wiles, that takes a simple form, but it's not particularly quantized or anything. So I view this as kind of like a no-go theorem. If you just have one electromagnetic field, in other words, if you don't have both magnetic and electric fields, or high order and electric field, or something more complicated, then Wiles are interesting, but not that unique compared to other materials. So let's try to find something maybe more interesting. Yes?
It's kind of a philosophical question. I mean, suppose I have a vial and I'm interested in it, and I anticipate that there's a bit of disorder around, so I must never ever use momentum.
That's more than a bit of disorder. That's a lot of disorder.
We're in topology, right, or topology stuff. I mean, and I want to probe my vial with an electromagnetic field in a linear regime. I mean, no nonlinear optics. And then I scratch my head and ask, what could happen? And I would claim the only response action you can get is chance-harness action.
So you're talking DC field, DC electric field?
Fixed frequency.
But I would.
No frequency. I don't want interactions, and as a fact, I know it's a chance-harness. So.
But if omega.
Let me
Okay,
finish my question.
sure.
Then, and the prefactor is a topological charge. So now it's down to a very universal level, and now I can start asking questions to this chance-harness, which will be very, very simple because it's chance-harness. I mean, the structure is quite simple. So wouldn't I get every answer, every possible answer from that?
I suspect not, because for one thing, okay, suppose I've got a strength of disorder that determines a tau, some Born approximation relaxation time. There are definitely higher order disorder effects, but I would argue that if omega tau is much greater than 1, I would be very surprised, for example, suppose I'm at extremely high frequency and all the electrons are doing is moving back and forth.
Low frequency stuff. I mean,
Exactly. So low frequency stuff, a lot of what I'm going to talk about disappears. So I think most of what I'm going to talk about, for example, to see this formula, and even the more exciting formula I'm going to come to, you should be omega tau greater than 1, which on the bright side is not that hard to achieve in some materials. I think omega tau less than 1, I can believe that all you're left with is some, I haven't studied it myself, but that sounds plausible what you say, but I don't think it would capture these things. So these are more high frequency.
You would say that there must be some response action to an electromagnetic field, and you're saying that at high frequencies it can't be chance-harness, or it must be somewhat more complicated.
I don't think so. I mean, I don't think it, well, let's see. Does it have to be, I mean, I think omega, I'll put it this way. There are definitely non-trivial omega dependencies of things. So those would have to appear as time derivatives of external A beyond, and I don't think it's just as simple as multiplying by A.
To lowest order is chance-harness, but then
Exactly. I guess I think that the omega dependence, yeah, I don't think, for the physics I'm talking about, it wouldn't be right to systematically expand in time derivatives, because these are definitely not perturbative in omega around omega tau less than 1.
But for peace of mind, I mean, at low frequencies we will still get a paramagnetic effect.
No, I don't think so. I think at low frequencies, if you just apply a wave, and if you're at omega tau less than 1, I think the effects go to 0.
No, but you apply battery. I want to apply battery.
But so a battery with electric field or with magnetic field?
Electric field, and I want to probe some.
Okay, so that's not chiral magnetic effect. That's just conductivity.
No, but isn't what they say? I mean, what they call paramagnetic
So
papers is a linear and B contribution to the DC conductivity.
that's chiral anomaly or something else. So chiral magnetic effect is usually just B, but E dot B does exist. Yes.
So then
Yeah. The one tricky thing, E dot B does exist, but a caveat is I don't think even at low frequency that E dot B, I mean, we did one calculation to try to show this. E dot B has multiple contributions, and the interesting topological one is not the only one, and it's not obvious that it's the largest one in that DC limit of a real metal. So I guess I mean, there are other people, Adolfo, who's here, has worked more on this than I have, but I am concerned maybe that E dot B is not necessarily the dominant effect. And so, for example, there are experiments that are interpreted in terms of the chiral anomaly where you don't see E dot B, you see more like E dot B to the third or something in the Engler dependence. There's an experiment by Ong in this category. So I wouldn't necessarily take that as proof of the chiral anomaly or something. Again, other people, this is an actively developing field where I don't think there's a consensus about whether the experiments are measuring E dot B physics. Good. Other questions? Okay, so on to nonlinear optics, and this is what I was saying about while. So a while point is a very simple object. You can make some 2-band model or 4-band model or whatever, so everything winds up being simple because there aren't that many parameters, but it might not be quantized. So for example, that chiral magnetic effect, even if you go to the time-dependent limit and so on, you get a non-universal factor, which is the splitting in energy of the 2 while points. So this is what I would call a non-quantized response, just like the anomalous Hall effect. So can we get quantized responses in metals? And the answer is experimentally, yes. It depends on how high your standards for quantization are, but there's a really cool experiment that is, I think, the best way to measure the fine structure constant with just your hands and a light bulb. And you need to have a friend who can make a sheet of graphene, I guess. But it's pretty neat, and it's kind of a proof of principle. And unfortunately, my blue is not showing up very well. But suppose you take a sheet of graphene, and people can make big sheets now, and you hold it up to the light. And you can mostly see through it. It blocks in the visible about 2.3% of the light. And 2.3%, it's not 2.3097. It's not like one of those quantum Hell measurements. The statement I'm going to make is not precise to 1 part in a billion. It's precise to about 1 part in 100. But anyway, it blocks 2.3% of the light, and 2.3% is pi times 1 over 137, where 137 is the famous fine structure constant. And it's the fine structure constant in vacuum. It's the real speed of light. It's not the speed of light for electrons in graphene or something. So that's my little existence proof that there are things you can measure in graphene. So that says, if you took 20 sheets of graphene and figured out how many sheets of graphene, say, it took to make 1 light bulb half as bright, you could work out the fine structure constant, which to me is impressive. So that's what I mean by quantized in a metal. And again, this is a little bit artificial. It only works for several reasons. It works because graphene is fairly clean. It works because the frequency range is not too high or too low. If the frequency were too low, you would be disorder dominated. And if the frequency were too high, you would be dominated by the fact that the bands in graphene are linear dispersing at small energy, but are not linear once you go away. So the effect I'm going to tell you is a bit like that, except it's a more nonlinear optics effect with a different quantum, but it depends on being in the right range of frequencies. Okay, so let me skip ahead a tiny bit. Sorry, I have newer slides. All right, well, I'm not going to look at my newer slides, but this is published in Nature Communications, and it's Fernando de Juan, Adolfo, Takahiro, me. So let me scroll back 1 minute. I somehow wound up with my old slides, I'm sorry. So here, the point of the effect is going to be take the effect that I told you before was a Berry phase measurement at low frequency and do it at non-zero frequency and compute the second order optics very carefully. So at low frequency, it's not quantized. It measures the Berry phase. It seems to agree with experiment, et cetera. Take a Weil semimetal and try to get into the following range. And you need to be in a region where in a material where the Weil points are split in energy. And there are materials where that's believed to happen. So far, there are not really big crystals of those materials that someone has measured optically, but that's okay. But what I'm going to flash up in a second is an answer for how much current do you put in when you shine light on a Weil semimetal in the following regime. The basic idea is going to be one Weil point is below the Fermi level, and in particular, these are the transitions induced by light at frequency omega. So the height of this cylinder is related to omega. If you jump up like that here, if you try to cross the Weil point, you can't actually make this transition because it's Pauli blocked. There already are electrons in the final state. If you go over here, then that transition is allowed. So all of a sudden, if you like here, once you've got a big Fermi surface, you're kind of in the semi-classical regime of this calculation. If the Fermi surface is changing by only a small amount, when I change energy by omega, then the old calculation works. If the Fermi surface is more or less, there are some details that could be improved, I think. If instead here, this is very far from the semi-classical limit because the nature of the Fermi surface is changing completely as you change omega. So what happens there? And the answer is and I should, to give credit where credit is due, this was noticed by the first three authors. You pull out some complicated formulas for second order optical response, and you do a more complicated version of what Thouless et al. Did in all these one electron things. The trick is to start off with a standard perturbation theory expression with energy denominators and so on, and play with it until you get something topological. And what they realized is that this is actually topological, and the result, and if someone can measure this even within 50%, I will jump up and down in happiness. There should be a approximately quantized nonlinear optics result with a quantum that is e cubed over h squared. So one of the points I made toward the end of the last lecture was that e squared over h appears all the time and means something in every dimension. If you want to go to one more power of electric field, so remember, this circular photogalvanic effect is a photocurrent, which means it's a current coming from the intensity of light, so it's J like E squared. And if you want J to go like E squared and you want something, well, some quantum, then you'll get E cubed, and then if you figure out what the other units have to be, you get an H squared C. So this would first of all be much stronger than this effect has been measured in the past, and second, it's a nice combination of fundamental constants. The other numbers are, so I should be a little precise here, what's quantized is the rate at which the light produces current. So it's dJ by dt. C sub n is the Chern number of a Weil node, or in an experiment, it would be the difference, the net Weil charge up to the Fermi level, say, if I can get in that range of frequencies I was before, and I is the intensity of the light. So this combination, you could measure this directly if you could do an all-optical measurement. If you actually measured it with contacts and measured DC photocurrent, which is more often done, then you'd have to write some kind of equation where there's also a relaxation time, and you would have to work out the relaxation time by other means. So again, it's also true that, like in that graphene experiment, we thought for a while, at least maybe someone else does, but I don't yet have a very good argument that this is not renormalized by interactions and so on, and we'd expect it to have corrections. So I mentioned in response to Alex, omega tau is kind of an important parameter for these, where tau is some relaxation time in the material and omega is omega of the light. So like in that graphene experiment, you need a pretty clean material, which means a pretty long tau. And if omega tau is greater than 1, then you're justified in starting with the band structure kind of clean picture. And then you'll get corrections which are order 1 over omega tau or 1 over omega tau squared, whatever, depending on the problem. So you need omega to be larger than 1 over tau. A nice thing about this result, it really is more topological than the graphene result, at least if I can only think about the two bands involved here. However, I curve this. Okay, corrections from higher bands would modify the statement, but it isn't just from linearity. It really is from the topological charge of the Weil point. Maybe that's a little technical. So there is some work since then, and let me call up one more recent slide. Because somehow I wound up using my old slides in the talk. Shoot. Ah, yes, this is what I wanted to show. So I have good news and bad news as far as experimental observation of this effect. So the good news is that there is an enormous observed nonlinear optical response in Weil semimetals. The slightly bad news is it's not exactly the one we predicted, and it's not in the material that we want people to look for. It's not the quantized one, and it's not this right circular versus left circular one. This is actually Tantalum Arsenide. This is kind of the Weil semimetal that everyone likes to study, the first one studied in detail. The problem with it from our point of view is that it has a lot of mirror symmetries. So if you want, it's not handed enough to get the effect we want because mirror symmetries give me positive and negative at the same energy. So it turns out that the total Weil charge at every energy in this material cancels out to 0, which means our circular photogalvanic effect is 0. But if you just do ordinary linear polarization optics and you measure what's an even easier second order effect to measure, which is just frequency doubling. So in other words, you put light in an omega and you measure light coming out at 2 omega, then what you get is a bit surprising. And this was the first paper. There's a second paper on the archive which is submitted by several of us. So you see effectively that this material has the strongest frequency doubling in a useful frequency range of anything that's been measured. So gallium arsenide, for example, is often used to double frequencies, and its value in the right units is about 350. This is about 10 times larger. If you go a little bit lower in frequency, it's more like 50 or 100 times larger. And as far as why, our best guess is that this is not precisely because it's Weil or topological. It more has to do with the material being strongly polar and maybe quasi-one-dimensional. But that's kind of inferred indirectly. Adolfo has a nice model of this material if you would like to know more details. But just as an experimental fact, it's kind of amazing. For those of you who know my collaborator Ornstein, he's a skeptical sort of person, and he describes this as the only experiment he ever did where the first time they measured it, the sample was so large it went to the roof of their oscilloscope, and they didn't know what was going on. They assumed it was an experimental problem, but then they confirmed it, and another group at Temple has measured the same thing. So at least as motivation for future work, this is exciting. It says there's at least one thing already measured in Weil semimetals that is quite unique. Although, as I said, our best understanding is that it's tough to directly link the magnitude of the second harmonic generation to the fact that it's a Weil. They're indirectly linked because being a Weil requires breaking inversion, as does second harmonic. And the fact that this is a very clear Weil semimetal probably has something to do with the fact that it breaks inversion strongly, which is what this is measuring. So what I'm showing you maybe for the moment is kind of the state of the art as of a year ago. There is a lot of other stuff happening. There are other measurements by Nilsson group. There's a lot of other theory. There's a lot of work on other materials that might show interesting nonlinear optical effects in this Weil class and so on. So I'd be happy to ask questions or have conversations about that as well. And as I mentioned, the other people involved in this work are mostly here today, so we could all chat. But I think that's about where I wanted to wrap up. I think if I had a bit more time, I had a bit to say about Majoranas, but let me maybe just wrap up with this, since I am about out of time. So what I talked about here was, in these couple of lectures, were really physics that you could understand with one electron and with thinking carefully about band structure. I believe that the phases I talked about, it's a bit tougher to prove this with metals, but at least for the insulators, they're definitely stable to interactions. Of course, there's a whole new family of phases that you get with interactions. But even if you focus on these fairly accessible, non-interacting phases, you can get particles and responses that were maybe conjectured to exist in particle physics, but don't actually exist there as far as we can tell. So for example, you can get that theta equal to pi magnetoelectric effect, you can get Weil fermions, you can get this amazing quantization and so on. So I find that personally kind of exciting. And the main subject for today was there are both Dirac and Weil materials in 3D, and that's a discovery in the last 4 or 5 years. I guess 4 years for Weils, 5 years for Dirac. So I guess maybe to end on that note, thanks a lot for having me here. I really appreciate it. It's great to meet up with some old collaborators as well. And thank you all for listening.
You mentioned very briefly the absence of
Well, it's interesting. So, yeah, the history is Halpern wrote a very scholarly, long paper on how you can derive this from Onsager. And various people have tried to make shorter versions of the Halpern argument, but I think the shorter versions are not rigorous in the way that the Halpern argument is rigorous, is my opinion. So I guess the two things that I think are correct, you can do the Halpern argument, or you can, if you want, at the one, so the Halpern argument is general to interactions and so on. Basically, the conditions are, if you have time reversal invariance and you're looking only at linear response, so you can use Onsager. If you were in some nonlinear regime, it's not clear that it has to be true. But I don't think there's a very, I think the efforts to make short intuitive arguments are actually wrong. If you want to compute it microscopically for one electron semi-classically, that's actually the first way that we stumbled across this identity. If you want, so that's saying, whoops. The reason why we were heavily invested in the truth of this little fact and spent a lot of time on it is that if this were not true, then you would get reflection at rotation. So somehow there are many consequences of this little, maybe better to put this previous slide, this fact at the bottom somehow appears all over the place. But again, this is now only one electron. But yeah, so if you want, okay, if you want more intuitive versions, there's a paper by Fried. There are one or two others. There's someone, I think Armitage wrote a little bit on it, but my own belief is that if you really want to understand, you should read the original Halpern paper, which is like 89 or so.